Now let's look at the next topic, how to determine the inverse of a function defined by a map or set of ordered pairs. So let's look at a definition first. What is a one-to-one function? Suppose that f is a one-to-one function, then corresponding to each x in the domain of function f, there is exactly one y in the range. Okay, you can think about y, because y is a function, right? That's why paired with x, we have exactly one y in the range. And corresponding to each y in the range of f, there's exactly one x in the domain, because function is a one-to-one function. And then the correspondence from the range of f back to the domain f is called the inverse function of original function f. The symbol is right as this. Okay, so put -1 on the right-hand side upper corner of the function name. Okay, for example, if original function write as f of x, and then the inverse function we write as this. Okay, be careful, this is not the same as function raised to -1 power. Okay, this is the symbol for the inverse function. Okay, so be careful of that. So what it means, the inverse function, so basically, okay, in the most easy words to say, just the x and y, they swapped the correspondence. Okay, before function, we say the mapping is from x to y, right? The inverse function is a mapping from y back to x. Okay, that's why the original function's domain, okay, actually is the inverse function's range. Original function's range actually is the inverse function's domain because the mapping is swapped, the direction. All right. So now let's look at an example. Finding the inverse of a function defined by a set of ordered pairs. Okay, so this is define the function, and then we want to find its inverse. So all we need to do is swap the x and the y for each ordered pair. Okay, so first point, original is -3, -27. The inverse will be -27, -3. Okay, for every point, we switch x and y. Okay, -8, -2, right? And then the third point, since x, y coordinates identical, so after we swapped, it's still -1, -1. And the same for 0, 0, 1, 1, right? We swapped, but since identical value can tell different. And then 8, 2, and then 27, 3. Okay, so find the inverse function if given by the order pair. All you need to do is x, y coordinate swap. All right, so find the domain of original function. Okay, domain of original function f. So this is an inverse function of f. Okay, if this is original function, we call the f of x. This is the inverse function of original. So domain of original function, we collect all the x coordinates, right? -3, -2, -1, 0, 1, 2, 3. That's the domain of original function. And then the range of original function is what? All the y's, right? -27, -8, -1, 0, 1, 8, 27. So what is the domain of the inverse function? Now, this is all the x of inverse, right? Which is -27, -8, -1, 0, 1, 8, 27, right? And then what is the range of the inverse function? That's all the y's of inverse, right? So that will be -3, -2, -1, 0, 1, 2, 3. So now you will see, right? Domain of original function actually is the range of the inverse. And the range of original function actually is the domain of the inverse because x and y swapped. Okay? That's the solution. And then what if giving you the map and the same thing, you just switch x and y, the column, okay, switch the two columns. And then domain of original function actually become the range of its inverse, and the range of original function becomes the domain of the inverse. Still the same concept, okay, xy swap. And then testing whether the two function is inverse or not, and then we can use the composite function to do the verify. Okay, is the inverse composed with original function, okay, must equals to the input x, and the other way around, original function composed with its inverse, and then also must equals the original input x. Okay, so why is that? It's just like a mapping, right? First, the mapping from x to y, okay, and then compose with its inverse, and then mapping back to the y to the x. That's why it's go back to the original input x. So let's look at an example, okay? Verify the inverse of this function is this function, okay? And ask you what value of x is this one, and what value of this is this. Okay, so let's verify first, okay? So f composed with its inverse. Okay, let's do that first. So that's equals f of x is the outer function, the inverse is the inner function, right? And then we plug in the inverse function by its definition. That's 1 over x plus 1, right? And then plug into the outer function, that's 1 over x minus 1, right? What is x? That's 1 over x plus 1. And then we simplify, that's 1 over x, right? Divided by number is equals multiply its reciprocal. That's why we got x. So what value of x is this? Right? What value of x is this? And then we just need to find the domain of the inverse function. Okay, inverse function is right here, right? So what value? X can be any value but cannot be 0, right? X can be any value but cannot be 0 because x is on the denominator. So it's like we're finding the domain of the inner function. All right, and then the other way around, what if the inverse composed with original? Okay, so what that means is inverse function is the outer function. Original function f of x is the inner function. Okay, and then we plug in the inner function by its definition, which is 1 over x minus 1. And then plug into the outer function. That's 1 over x, right? Suppose here's x plus 1. What is x? I'm sorry. X is 1 over x minus 1. So again, 1 divided by a number is equals multiply its reciprocal. That's why we got x minus 1 plus 1. And then that's equals x, right? So now we proved actually these two functions, they're inverse functions. And then what value of x is for that? That's looking for the domain of inverse function. So what is the domain for inverse function? Denominator is x minus 1, right? So denominator cannot be 0. That's derived x cannot equals positive 1. All right. So you can look at a solution as the same, right? X cannot, this is, the book did the inverse compose with original first. I did the original compose with inverse first. That's why it's kind of switch. It's the same, right? Same answer.